Hi, this is Owen Astrachan with videoM, linked lists for CompSci 201, academic year 2021-2022. M is for method. In Java, a function is called a method. In other languages, we often call them functions. M is for meme. There are so many. For malware, malicious software you likely download unintentionally, and for machine learning, how math and computer science are changing the world with huge amounts of data and a need to be ethical in using it. This is a reminder that we've seen it briefly, the killer app for linked lists, low-level nodes, a simulation of recombinant DNA or polymerase chain reaction, and with nodes representing each nucleotide or a group of nucleotides in a strand of DNA. And in the simulation, you will see string strand, which takes lots of time and runs out of memory, and string builder strand, which takes less time but still runs out of memory, and all of them are dwarfed by the efficiency in memory and time for this linked strand class that uses low-level nodes. This is an example of better use of time and space, which is atypical. Often there's a trade-off, time and space. And this is a review of the nodes that you'll use in implementing that assignment and in many other applications as well. In any data structure course, you are going to be expected to program with these low-level nodes, a little structure that stores some information and a pointer to another node. We'll see this again with trees. They are common low-level structures used to implement other data structures. And in 201, we'll solve the P4 DNA link problem, as well as APTs and other problems that leverage these nodes. Now, to remind us of how these nodes work, it's often a good idea to look at something we do know, and that is how to sum the values or the lengths of the strings, for example, in an array of strings. And we're going to look at that as something we do know how to do to understand the code that will add up all the strings that we see here in this linked list. So that in this linked list of 3 nodes, adding up the lengths of ant, clever, and prose will give us 14. We'll write code that works with any number of nodes and any strings in those nodes. Just as a reminder of the code that loops over an array, we have a for each loop to look at every string S in the array list, and we accumulate a sum by adding the length of the string that's in each array slot to this running total, and then we return it. That's reasonably typical, I hope. And now we'll look at the code that uses a linked list to do the same thing. We can't use a for each loop because a node is not an iterable. It's a low-level construct. It's not standard Java, and we're not making it implement any iterable interface that will allow it to be part of a for each loop. Typically, the node class would be nested in another class. You'll see that with P4, or it might be in the same project so that it's essentially imported. We'll see that when you solve APTs that use linked lists. In the example that we have here, our nodes store strings, but they could store an int or any other information. How do we access these node fields? Well, we refer to either info or next. And because these are just plain old objects, we don't have getter and setter methods. We just access directly info and next. And so we see here the code that will loop over this linked list referenced by variable first by calling total with first as a parameter. And what we'll see then is that list, the parameter in the method, is a pointer to the first node because the variable first is passed to total, and then list in method total points at the same node. We check to see that list isn't null. We go into the body of the loop and we evaluate list.info.length. That's the length method applied to list.info, and we can see in our diagram that that will be 3. So when we add that to total, total will become 3, as we see in our animated slide. Then list gets list.next. So first we evaluate the right-hand side and we say, what is list.next? Well, we can see in the diagram that's a pointer to clever. And so list will now be a pointer to clever. And we'll continue to accumulate the sum by adding the number of characters in clever to 3. That will make it 9. And then when we implement list gets list.next, it will move to the next node. Now we will add the length of prose to total. That will make it 14. And when we use list get list.next, by implementing and executing that, we will point at null. The loop will end because list is now null, and the loop only iterates while list is not null. It will exit and return 14. In addition to traversing a list, sometimes we'll want to change the list. And when we change a list, we'll need to assign to a next field. And in this code, we'll walk through an animation, but we see that the loop test is slightly different. It says list not equal to null and list.next not equal to null. And what that means conceptually is that list points at a node and list.next points at a node, because both of them aren't null. So this list must have at least 2 elements, the one referenced by list and the one referenced by list.next. And what we'll do is, while they're 2 nodes, we'll walk through the loop, and we can see that we're going to use our standard list is assigned list.next update to move to the next node. But before we do that, we're going to change what list.next points at. In essence, we're going to chop off every other node from this list. And let's see how that works by looking at an animation. So what we have here is we're going to chop this list of 4 nodes: ant, clever, prose, prose. And when we chop it, we're going to see, okay, list.next is assigned list.next.next. Now, with 2 next, how do we figure that out? Well, it's the next field of something. Of what? Of list.next. And what is list.next? Well, that's the next field of ant. That's clever. So list.next.next is a pointer to prose, because it's the next field of the thing pointed to by the next field of the thing pointed to by list. List.next is clever. List.next.next is prose. So I have a pointer to prose on the right-hand side of the assignment statement, and I assign list.next to that. So the picture we have is list.next points at that prose node. And now I'll move list and assign it to list.next. Well, look at the picture. List was ant, list.next is prose, so now I move list. And then I evaluate the loop test again, and I see there are 2 nodes, prose and then the second prose. And so I go into the loop, and again I evaluate the right-hand side, and I see that that's list.next.next. That's actually null. So the next field of the thing referenced by list, that's list.next on the left-hand side of the assignment operator, that's prose's next field, it will become null. And then I'll advance list to the end, and the loop will finish. One more example, adding nodes to a linked list being constructed from nothing. I'm going to convert an array of strings to a linked list of strings. And I have a special case that we can see above the highlighted node that says if there's nothing in the array, return null. That way I know I won't have an index out of bounds exception when the highlighted line is referenced, because I know there is a element whose index is 0. And I create a node from that string, the string at list sub 0, and I point first at that. So first is the first node of the list. And then I'll say last gets first. So my picture will have both of these. First points at a new node, and last points at the same node. And now I'll iterate over the rest of the strings. I had to treat the first node separately because I need to return a pointer to it. And now I'm going to advance last as I iterate through the loop. Once again, in an assignment statement, I evaluate the right-hand side. New node list sub k null. That creates a new node. K is 1, so I create a new node storing clever. What points at it? Last.next. So my picture becomes ant followed by clever, because last.next is the next field of the thing referenced by last. And then I'll move last, so now it becomes clever. I'll iterate again, make a new node, this time containing pros, and I'll make last.next point at that node. Now my loop is finished. I return first, which is why I had to create that first node before the loop to anchor the value that I was going to return. When you want to create a node, you must call new. Don't call new unless you want to create a new node. Sometimes you'll just assign one pointer to another, but if you want a new node, call new. If you're going to change a list, there must be an assignment to a next field. You can't make a new list built without assigning to a next field. You might call new 10 times, but if you don't link things up by assigning to a next thing, a next field, you won't actually build a linked list. Often, extra variables are useful to help you reason about the code. This is Barbara Liskov, a Turing Award winner in 2008 for contributions to practical and theoretical foundations of programming language, system design, data abstraction, fault tolerance, and distributed computing. There's a Liskov substitution principle that's foundational to object-oriented programming. And what she says is, the advice I give people in general is that you should figure out what you like to do and what you can do well. And the two are not all that dissimilar, because you don't typically like doing something if you don't do it well. So you should instead watch. Be aware of what you're doing and what the opportunities are. Step into what seems right and see where it takes you. I hope you enjoy your journey. Happy programming.